These are the solutions for finishing off problem number 12 through 15 on the study guide for chapter 4. And so we worked on the first part here in the last tutorial, and that asked us whether the triangles were similar. And then the second part says, at what height in meters should Matt hit the tennis ball? And so this is what we're trying to find, this distance right here, x. And so what we're going to do is set up a proportion for this to solve. And so we'll go ahead and do the height of the net, 0.9, over the distance from B to A. And so that is 6. And then from there, I want to set up this next triangle, so I find the side that corresponds to CB. Well, that one is going to end up being this one right over here. And so E to D corresponds to CB. So I'm going to put that letter that represents that variable that represents that distance on top of the fraction, since I put the height of the net on top of the first fraction. And then I put this distance, B to A, in the location of the denominator. And I'm going to do D to A here. So I've got to take 6 and add 12. And so that's going to be the part that you got to make sure you do. And so 0.9 over 6 equals x over 18 is what I should have. So I'll go ahead and cross multiply here and multiply the 0.6 by 18. And I could take out a common factor, but I'll just leave it the way it is for now. And so when I do 0.9 times by 18, and then the other part is going to be this, x times by 6, so 6x. And so I take 0.9 and multiply it by 18, and I get 16.2 equals 6x. And so now I'm ready to do the division and divide by 6. And so off to the side, I'll do 6 into 16, 16.2. And so 6 goes into 16, we have 2 times, and that makes 12 with 4 left over. Bring the decimal point straight up, and 6 goes into 42 7 times evenly. So 2.7, so let's go ahead and write that as a little sentence, so we can say the ball should be 2.7 meters above the ground when Matt hits it. Alright, well, let's take a look at the next problem. And so it's on the other side of the page, and it says prove whether the shapes are similar. So here we're not given the angles, and actually we do have the angles because it looks like these are right angles. But just because these are right angles, all right angles here, doesn't mean that the shapes are similar if we're not dealing with a triangle. If it were a triangle and all the angles were the same, right away we'd say, oh yes, the shape is similar. But with a shape that's different than a triangle, like a rectangle here, we have to look at the sides. So we have to see if the sides are proportional. So that's what I'm going to do here. I'm going to take this 8 right here and compare it to this 6, because they're kind of in the same location with respect to the right angle symbols here, and the sizes look about the same. So 8 is to 6, I'm going to say. And now another side that should be proportional to those corresponding sides would be this one here. This 10 and this one, this 8. So I'll see if it's the same as 10 to 8. Well, there's 2 ways to see whether these two ratios are proportional. We could either reduce them or cross multiply. And I'm going to choose to cross multiply here. So I'm doing 8 times 8, and I'm setting that equal to 6 times 10. And I see when I'm cross multiply, the numbers do not equal. And so what that tells me is that the shapes or the figures are not similar. So we'll say the shapes are not similar. And the reason would be because the corresponding sides are not proportional. So if the figure is not a triangle, we have to check for this. We have to see if the sides are proportional. And because the sides are not proportional, that means it's not a similar figure. Let's take a look at the next one here. We're supposed to prove whether these shapes are similar. So on this one, we don't have the angles. And So I'm having to use this proportionality of sides again. So let's check this one here. Now, if all the angles were the same, I'd be able to say, oh yes, it's similar because this is a triangle. With the rectangle, I cannot do that. I have to check for similarity of the or proportionality of the sides. So I'm going to do the same thing here. So I see this is AC and this is A prime C prime. So I'm going to do 6 over 4. So definitely those two sides correspond because of what the variables say they are. And then I'm going to go ahead and use the reducing method this time. I'm going to divide each by 2, and I end up with 3 halves. So that means I need 3 halves with all of the corresponding sides. So let's take a look at another set. CB and CB. So C prime, B prime is 3, and CB is 2. Well, that equals 3 halves, obviously, so that's good. And then let's check the last one. A prime, B prime is 4.5. AB is 3. Now notice I have to make sure I'm staying consistent. I'm putting the ones that were the image, the one that was transformed, I'm putting that on top, and the pre-image I'm putting on the bottom. As long as you're consistent, it doesn't matter whether you have 2/3 or 3 halves, as long as you're consistent. Now this one seems tough because of the decimal point, so let's get rid of that decimal point. The way we can do that is we can multiply it by 10. And it'll make the numbers bigger, and we'll have to reduce again, but at least we don't have the decimal point there. So now I'll go ahead and take out that common factor. Now the big number is 15, but if you didn't see that right away, you'd see a 5 and then eventually a 3, and you get to the same number I'm going to get to here, which is 15 goes into 45 3 times, 15 goes into 32 times. So notice how each of these has a ratio of 3 halves, each of the corresponding sides. So we'd say the triangles are proportional, or are similar, let's say that, because they're proportional. The triangles are similar because the corresponding sides are proportional. So again, that is one way to determine similarity. Well, the next problem says, prove whether the triangle ABC is similar to triangle DEF. Well, let's take a look at it. So I've got some sides here, or some angles here instead of sides. So I know this is 60 and this is 90 degrees with the symbol they give me. So I'm going to go ahead and add these two angles up. So 60 and 90 add up to make 150. I'm going to subtract that sum from 180, and that's going to give me 30 degrees. So I know this angle is 30 degrees. Well, once I've got two angles that are the same, like this one's 30 and this one's 90, this one's 30 and this one's 90, I know this one has to be 60 degrees also. Now the reason is that they have to add to make 180. And 30 and 90 makes 120 plus 60 makes 180. So what we can say is, since the angles are the same and we're dealing with a triangle, that means we have similar figures. And so here's my phrase I'm going to say. We'll say, since two angles in one triangle, since two angles in this one triangle here are congruent, so they're congruent to two angles in this other triangle. So they're congruent to the two angles in the other triangle. We can say, then the triangles are similar. And the reason why we can say that is because of the angle-angle property, or postulate, we'll say. Similar by the angle postulate. And the postulate, again, is just a rule in which we don't even have to prove because we know it's true. And so that's the case here. And so those are the types of problems you're going to see on this chapter test. Good luck.